Welcome back, everyone, to the last day of this workshop. This morning, we'll have Kiran Luecke tell us about complex orientations and fixed points.
Yes, thank you. So, as most of you guys know, this talk was supposed to be given by Shahar Carmeli, who unfortunately couldn't make it. He asked me to say hi to everyone, and he also apologizes for not being here. I told him he obviously doesn't need to apologize for not being able to make it. The silver lining is that he was going to talk about joint work with me, so instead I'll talk about joint work with him. So mathematically, it will be the same talk. Okay, so it's Friday morning. Let me start nice and slow. Let's consider the total Turing class. So here z is some dummy variable of degree 2. And we know from the Whitney sum formula that this takes direct sums to products. So C of B plus W is C of B W, which can be neatly captured by saying that this produces a map of H spaces like that. Okay?
The GL1 is applied to the whole group ring, not just to the
Yes, GL1 of the whole ring. Okay, so here's a question. Both the source and target, if I just write them in lowercase, they become infinite loop spaces, not just H spaces. And the question is, can we lift this total Turing class to a map of infinite loop spaces? Does anyone know the answer? Which answer do you know? Well, I guess in this form, there's only one answer. But
depends on the choice of infinite loop structure.
Very good, yes.
GL1.
So I've sort of, in some sense, specified it into infinite loop space structure here. Oh, first of all, this question is an official question of Graham-Siegel from 1935. And the answer was given by Snaith, I think, in the same year. The answer is no. And proof is very simple. If this were an infinite loop map, then it would have to commute with the transfers for finite covers, and Snaith just produces an explicit finite covering for which this formula doesn't commute with those transfers. Okay, and then there was, I think, roughly a 20-year span of work that culminated in another answer to the question. And this time the answer is yes, as long as you change the target slightly. So yes, this is due to Lawson et al. They construct this infinite loop space geometrically, so they build it in sort of a point set model for spectra out of algebraic cycles, so some algebraic subspaces of projective space, and they show that this infinite loop space admits the total Turing class as an infinite loop map. So the first half of today's talk will be an alternative yes answer with maybe a more familiar target to the audience here. and it's going to be the Tate fixed points. So here T is the Lie group. A1. Okay? And as a sanity check that this is the right thing to even receive such a formula, recall that the homotopy groups of this thing is a Laurent series T, where T is degree -2. Okay. So the first half of the talk won't be super hard. We'll sort of just we'll introduce some games you can play with Tate fixed points and complex orientations, and get a total Turing class lift. And then the second half of the talk will be exploring some consequences of this type of thinking. All right. Any questions so far? Okay, so let's recall some bag of tricks. These are fairly standard things. So the first one is the Thom spectrum functor. So we have a functor from connective spectra over pig. Oh, hang on. Before I do this, I wanted to maybe drop a hint for why you would expect the Tate fixed points to show up when you're trying to lift a total Turing class. So first, Shahar and I were thinking about, hey, can we lift the total Stiefel-Whitney class first? And that one is much easier. So if you want to lift the total Stiefel-Whitney class, that's much easier for two reasons. The first reason is this formula for Millian-Stasheff that everyone probably knows, that the total Stiefel-Whitney class can be gotten by taking the Thom class of a vector bundle, applying the total Steenrod square, and then taking the Thom isomorphism inverse. So formula is that WV is theta V inverse square of theta V. Okay? That's one fact. The second fact is that there is a gadget that implements the total Steenrod squaring operations, and its target is C2 Tate fixed points, and it's called the Frobenius. And so from putting those two facts together, you can very quickly lift the total Turing class to a map to GL1 of F2 TC2. And so then we wanted to do the Turing class story, the complex story, and so we needed some sort of S1 Frobenius. But of course, such a thing doesn't quite exist, so the story is a bit longer for the total Turing class. Okay, so what are some tricks that we'll need? So let's recall the Thom construction. This lands in E infinity rings. It takes an element x like this to the Thom spectrum, which we can say define as the colimit of the composite to spectra. What will be most important to us is the following property, mapping out of a Thom spectrum in the world of E infinity rings to some other E infinity ring R. The space of such maps is equivalent to the space of null homotopies of the composite of this F and the unit map of R. Okay. And then the second bit of machinery that I'll introduce is this GL1 adjunction. So there's the lowercase GL1 that I used up there. It's the higher algebra analog of the units in a ring, and its left adjoint is usually written like this, a group algebra type thing, and perhaps some people prefer this notation. And the target is connected spectrum. Okay? And of course, the adjunction means that there's a mapping space adjunction. One more important thing that I will use a lot is that if this is non-empty, then by this adjunction, it's a torsor for map Okay, the way I think about that is, well, if there is a null homotopy, then the space of such I can identify with this space. If I take any two null homotopies and I can compose them to get a null homotopy of the constant map, and null homotopy of the constant map is a map to the loop space of your target. And then by the adjunction, this adjunction, we find that it's also the same as ring maps like this. So far, so good? Okay. So now let's move to complex orient. Oh, let's do some examples of Tom spectra. So the most important examples for me today will be mu pointy brackets n. This pointy brackets n doesn't mean the same thing as it does for BP pointy brackets n, but it's just the standard notation. These are Tom spectra of connective covers tau greater than or equal to n. Okay, so there's a J homomorphism from Ku to pick S. This sends a vector space to its stable one-point compactification. I can restrict it to Whitehead covers and take Tom spectra, and these are what the MUNs are. So for example, MU0 is what we usually just refer to as MUP. MU2 is MU itself. And then the next one, MU4, is MSU, and so on. Okay. All right, so now I'm going to set up some complex orientation theory for categories. The reason that we needed this was that, we knew we needed to be working with some Tate constructions, and there's this slight problem that taking Tate fixed points is only lax symmetric monoidal, and this caused a little bit of a headache and requires us to work with some orientations of categories, which I will explain now. So first, we define the complex orientation of a category. So let C be a presentably symmetric monoidal category. That means it comes with a unit map from finite spectra to C. And define the space of orientation of C. To be the space of null homotopies of its J homomorphism. So I have a map BU to pick S, and I have the unit map, which induces a map.
Is C stable?
Yes. I think I got exactly that question the last time I gave this talk. Definitely. C for me will almost always be perf of some ring or its categorical Tate construction, as we will see. Also, I should mention, in case I get harder category questions, between Shahar and I, the person that actually knows category theory is Shahar. So. Okay, so stated like this is actually no more general than, this complex orientation story, just an E-infinity map from MU, because all this definition really sees is the endomorphisms of the unit object of C. So you haven't gained any generality with this, but the next thing will. So now we want to introduce some S1 actions again, okay? So now, we want a unit map of C with some S1 action, okay? So I ask for such a map, which is exact, symmetric monoidal, and preserves finite conos. Now I'm going to define the space of projective orientations of this thing. Or per C phi to be the space of null homotopies of, okay, I'm going to take that diagram and just some of this diagram and raise it to the btth power. So this just takes a vector space with an S1 action, and it takes its usual stable one-point compactification, which now also has an S1 action. Now I can use my doodad phi to map to pic C. But I don't want to consider null homotopies of this map because I still want the domain of my map to be BU. I want it to be closely related to complex orientations. So I want to precompose with such a map. Given that I've called it a projective orientation, does anyone have a guess for what this map is going to be? I talked to someone at coffee the other day who guessed it.
Yeah, that's scalar.
Yes, you remember the scalar multiplication action. So we can write that as tensoring with the standard representation of S1. So this just sends V. Sends V to V tensor L. You just remember how the scalars act on V. That will go to a sphere. The underlying spectrum looks the same as it did before, but now we remember the S1 action, and then we do whatever phi does. Okay. Here's an example of a data C comma phi. C I take to be perf R Tate outside. So this is the categorical Tate construction of perf R. So it's the quotient of cofiber of the norm, categorical norm map from perf R BT, the constant colimit on BT to the constant limit. So it's not the same as perf of the Tate construction applied to R, but it's close enough in the sense that the endomorphisms of the unit object in this category are the usual Tate construction on R. The nice thing about this one is that it fixes this problem I mentioned earlier, the Tate construction as just a quotient map from this thing to the cofiber that is symmetric phenomenon. Okay, so we take phi to be the quotient map for perf. Yeah.
Should there be like a suspension on the source or something? Like because it's the sphere. Sorry, S1.
I'm not sure. I don't think so. Like the constant shape color? Maybe. Again, Shahar is the one who knows.
No. It's kind of presentable categories, so it was also the same as different products.
Oh yeah. Thank you.
Okay. So this is the map that take. Let me write it in the next one. Other questions? Okay, so this is the only example I will be considering of such data C and phi. And now the key lemma is that for any R, this pair of data is canonically, projectively complex oriented.
canonical tape construction, if you apply when R is equal to the sphere spectrum, does it become any easier to describe then, or is it the same?
I don't think so. It's the same. Yeah.
It doesn't mean what is the space of orientation is contractible, what you say.
No. Just there is a preferred one.
Point, yeah.
I will tell you what the preferred one is. Okay, so let's just draw our diagram that we need. I will be drawing this diagram a few more times in the talk, probably. So the diagram now takes V to V tensor, standard representation, then to the representation sphere, and then what it does, what this guy does, right, is it takes the representation sphere, tenses it with R, and then takes the fixed points of the whole guy. So notice that this is not like the J homomorphism of RTS1, which would only take Tate fixed points of R. This Tate is now also remembering this action that we put onto every vector space. And it was actually this functor that we, came up with first, and we knew it worked in practice, and then Shahar made sure it worked in theory as well. Okay, so we need a canonical null homotopy of this functor. And the answer is just that the universal property of the Tate construction gives us one. The universal property of the Tate construction is that it kills induced things which are like freely S1, have a free S1 action, and well, a vector space, everything except the origin has a free S1 action when you're acting by scalar multiplication. So this thing, as far as the Tate construction can see, is just a zero-dimensional vector space. Okay. So we call this null homotopy one you get from the universal property of the Tate construction, the Euler orientation, because it's like an Euler class. Okay. The next key fact is, so that worked for any ring R. Now, if R was itself already complex oriented in the usual sense, then I have a second projective orientation in the game. How do I take the usual complex orientation and get a projective one? Well, the usual complex orientation is a null homotopy of the usual J homomorphism, which occurs if I just like delete the exponents on these three lines, right?
Is this an E infinity orientation?
Yes, always E infinity. Yep. I will just, for the rest of the talk, if I just say orientation, I almost always mean E infinity. I think always. So yes, so I have a null homotopy of this without the exponents, and then I can just, post-compose with the Tate collapse, this guy, and pre-compose with my map like this. So I get a null homotopy, which I'll call Tate, then omega to the BT, and then, I didn't give this thing a name, tensor L. Okay, and so now we're in this situation that I sort of mentioned over here, that we have two null homotopies of the same map. It's not the J homomorphism anymore, so we have two null homotopies of this map, and so we can compose them and see what we get. Let's define. We call this the Euler-Tate Chern class. the division of these two null homotopies, which becomes a map from the same domain, but now the loop space of the codomain. And as I said before, endomorphisms of the unit in that guy are still just the usual Tate construction. So the loop space is what I want it to be. Okay.
Could you explain again why you get that second
Yes. So how do I get the second orientation? I take my given orientation, the infinity orientation, I think of it as a null homotopy of the usual J homomorphism, which appears in this diagram right here, but without the exponents. And I just like raise it to that power. That's W to the BT. And well, that would be if I like had BT here. Then there's a map from BT to T power. That's this. So I have a null homotopy of a diagram. The middle of the diagram I can pre and post compose. Okay, that's the Euler-Tate-Chern class, and here's okay, it's some abstract nonsense so far. Now, here's some actual formulas. The Hertzebruch series of the Euler-Tate-Chern class is, well, first of all, what is a Hertzebruch series? This is a very classical thing. Maps like this, from BU to GL1 of something, are referred to as stable exponential characteristic classes. And from such a thing, you get a Hertzebruch series, which just means evaluated at the line bundle, the canonical line bundle, so L minus 1. So here, x is the coordinate of so using the complex orientation of R, I get a coordinate on R on the Tate construction by using the unit map of the Tate construction. I also get an identification of the homotopy groups of the Tate construction as a Laurent series as before for Z. And the complex orientation also gives me a formal group law, and I claim that the Hertzebruch series in those coordinates is given by this formula.
Can you explain the formula?
Yes, so it's x plus t in the formal group law.
The plus and the t were very similar.
Oh, sorry, yes.
Thank you.
Okay, and the proof is quite simple. What do we need to do? We're composing two null homotopies, which in this framework means we're composing two identifications of this functor with the constant functor. Okay, one identification proceeds via the given complex orientation of R. So I'm like doing the complex orientation inside the Tate fixed points. V tensor L, I think it's best, the way I like intuitively think about what's going on here is I have V is a vector bundle over some space X, and then V tensor L is a vector bundle over X cross VT. Just the external tensor product of the two obvious bundles here. Okay, so I've done a Thom isomorphism in my orientation omega to get here, and then on the other side I have the Euler orientation, which, what does the Euler orientation do? It says pull back along the zero section, and the Tate construction just makes sure that that's an isomorphism for you. So this composite is Thom isomorphism, pull back along a zero section, that's an Euler class. And if I do the case that V equals L minus, oh, there's two L's in the game. This is the L corresponding to X, and this is the L corresponding to T. Okay? And the Euler class of this bundle, the Euler class of Lx is X, that's how I define X, and the Euler class of L sub T is T, that's how I define T, and then the Euler class sends sums to products and inverses to divisions, and so this is X. Oh, it sends tensor products to the formal group law, so I get okay. Oh, not bad. Questions? And so now we've lifted the total Chern class. Why? Because now we take R equals Z, and we get the Euler-Tate guy in this case has Hirzebruch series. Just literal X plus T over T, or 1 plus T inverse X. That's now our Hirzebruch series, and this is the Hirzebruch series of the total Chern class. This is another way to say that the Chern classes are the symmetric functions in the Chern roots. It's that very classical story. Okay. So that's the lift. That's the lift of the total Chern class. So up to here, this is kind of not real math. Maybe this is idle. Shahar and I idly noodling about a question that was already answered in 1975. But we had a lot of fun doing it. And surprisingly, now this type of thinking will allow us to answer some real math questions. So that is what I'll do for the remainder of the talk. Any questions so far?
Maybe a bit of a basic question.
Yeah.
Before you presumably erase that, could you just remind me why MX carries a unit algebra structure? So it makes sense.
Not really. The way I think of it in my favorite case, which is VU, is you, like, and this works for anything that's connected, is that you're like, you can use the adjunction to get, so BU to GL1S, a BU to pick S, you can loop it to get an action of the unitary group on the sphere through E infinity ring maps, and you can take the quotient of that in the E infinity world. And that's MU, and when you say it like that, then it's like, well, 1 clearly an E infinity ring, because I took a push out in E infinity rings, and 2 clearly has this property. And I think you have to be a little fancier if you want not just connected things, but connective things. But it's the same type of deal. There's a paper by Toby Bartel and, oh, well, that's for the universal property. The fact that it's an E infinity ring goes back to May, very far back.
The thesis we want to do is actually.
Oh, thank you.
Why should we have GL1 as the target for this? Philosophically, why is it GL1?
Yeah, because the total Chern class, I didn't invent the total Chern class, but it starts with a 1 plus blah, 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 and it's multiplicative. And so GL1 is the perfect home. Actually, the perfect home is SL1, meaning that it starts with, like, the 0th term is literally 1, but let's not get into that.
Can you hold down that board over there? Even though
Yes. Oh, I can.
do that too.
Okay, so for the applications, let me rephrase slightly what we were doing. So, the applications are going to be to like usual complex orientation theory, so I want to sort of shift away from this weird projective stuff. And how are we going to do that? So we're going to draw the same, oh, no, just rewrite it. We were considering this type of diagram where this first step was tensoring with some representation W. So we're doing this. Sorry. To connect back for this construction to like give us something about complex orientations, null homotopies of this need to correspond to null homotopies of the usual J homomorphism, which means that we'd like this composite to be hopefully canonically homotopic to the usual J homomorphism. And what we'd like is that the inclusion of like the 0 element of W is an equivalence. Okay? And so what does that mean? That means that W should be of the form a trivial representation of some of G, which used to be S1, but now we generalize, and something from the form W prime. And we just need that the Tate construction, whatever it is, it's the cofiber of some norm map. We need that the orbits that occur in the unit sphere of this representation are killed by that Tate construction. And then we do the same Tate vanishing game, and we see that this is still the J homomorphism. Right, so what we're doing is we're taking the J homomorphism and twisting it by a representation which in the Tate construction untwists, right? And now we can do a bunch of fun stuff with this, okay? So the first example is we take G still to be S1, and we take W to be C minus L. Okay? This one is extra special because it's a zero-dimensional representation, which means that I can actually start from KU. Tensor with, I'm just going to abbreviate it as 1 minus L, go to BU, BT, and do my usual game to take R. Okay? And so this means that I can do this same construction, but now instead of just with L, with 1 minus L. Start with an MU orientation, a null homotopy from BU, and end up with a null homotopy from KU. So this takes we get a sharp construction. We'll see in a moment why I call it that. We go from MU orientations R to MUP orientations. Call this one omega. So it becomes sharp 1 minus L. Of the S1 Tate fixed points. Okay? And I call this sharp because this, in the case that E is even periodic, precisely recovers the construction of Ando French and Nora Ganter, which they call the sharp construction. They define this in terms of formal geometry. So they use theta structures on the line bundles over the formal group that you get from the sheaf of invariant differentials, that type of thing, the whole like symmetric co-cycles story. So they define a sharp construction in those terms for even periodic things. This sort of abstract nonsense geometric thing recovers exactly that construction, and it gives you that construction is E infinity. So if you input an E infinity orientation to the sharp construction, you get an E infinity orientation out. And so Ando, French, and Ganter use this sharp construction to construct an especially interesting orientation, which is the sharp construction applied to the string orientation.
Sorry, so you
subscript for sharp is just 1 minus L.
1 minus L, yeah, because that's the that's the representation W that I use,
Okay.
yeah. The Jacobi orientation. This is an orientation that has received a lot of interest both in the past by people like Borisov, Lubgober, and that crowd of people. They refer to it as the two-variable elliptic genus, and it also seen a recent revival in the work of Lin and Yamashita, and also in sort of mathematical physics adjacent. It is defined by Ando, French, and Gunter to be this sharp of the string orientation. So it's a sharp of an mu6. Oh, I should say, so I went from KU to BU, but I can play the same game between any two levels of the Whitehead Tower of BU. So I can start with like BU6, apply the sharp, and get one better. So BU4, which is MSU.
What about KU and BU? BU is
So yeah, little ku is like the group completion of complex vector spaces. BU is its two connected cover, and so on. I get that it's in the infinity orientation. So that's nice. You know, E-infinity orientations are difficult to come by, and now we have a new one in the game. Okay, next we have another application of the sharp construction, and you'll see why I'm especially excited about this board. We can recover the result of Hovey and Ravenel on the chromatic support of MON. There's another thing I can do. We fiddle with the group G up there, and we fiddle with the representation W. I can also change my ground field from the complex numbers to the real numbers and do everything with real vector spaces and BOs and stuff instead of BUs, and it's the exact same game. Theorem is that at p equals 2, MON is T phi n, I think minus 1 acyclic, where phi n is the number of non-vanishing homotopy groups of BO. Okay. Hovey and Ravenel's proof is oh, first let me give this proof. So let R1 be MON, and then Ri. So let's just take iterated TC2s of MON. We use the real analog of this result, that each time I take a TC2, I get a one better orientation of MO. I find that, right, so R2 is MON minus 1 oriented, Rn is MO oriented. MO is an F2 algebra, so it's T0 acyclic. A famous result of Jeremy, if you're E-infinity and your Tate construction is TK acyclic, then you already were TK plus 1 acyclic. and we iterate back up the tower and find that MON is Tn minus 1, acyclic. And then we can immediately improve the bound to T phi n minus 1. Well, because we're like jumping down the Whitehead tower of BO, and if like the next homotopy group is 0, I don't need to take a Tate construction to get a better orientation. The next ring is just like the same as the previous ring. So you immediately improve to T phi n minus 1. Yeah? And so here I can say how my talk is related to the telescope conjecture. I have the telescope appearing. I have the guy who came up with the conjecture. And I have one of the guys who solved the conjecture. What more can you add? Questions so far?
What representation to replace? So in the complex case, you use 1 minus L, which I think of as the K-theory orientation of complex vector bundles. So what representations do you use in order to improve the connectivities in the BO tower?
1 minus the sign representation.
So that probably handles the ADAs. Does that also do the jump from 2 to 4 and 4 to 8?
I'm sorry, I don't quite understand.
Okay, well, I can see how that gets you from KO to BO, or from BO to BSO, but then I'd like for BSO to be spin. Or from B spin to B wave. I thought that it might involve the idea of Shapiro orientation for real case theory. It sounds like I'm misunderstanding.
Yeah, maybe we talk after, yeah. Okay, so next application is please. Now we can also answer. So Jeremy and Alan have this paper where they show that MUP, periodic ordism, atomic spectrum of KU, is not equivalent as an E-infinity ring, not even as an E5 ring, to MUP in the presentation as Snaith gave it, so as the group algebra of BU with the bot class inverted. And in that paper, they ask a bunch of questions about like what types of things are oriented by MUP, the usual MUP, atomic spectrum MUP, and what types of things are oriented by the Snaith MUP. So, first, Snaith showed. Take the group algebra of BU, and I invert the bot element, hanging in pi 2. But this is the same as a homotopy ring spectrum, MUP. Okay. And Han and Yuan showed that this is not true as even E5 ring spectra, so in particular not as the infinity ring spectra. I'll call this MUP Snaith. Okay. Now we have seen, we can apply the sharp construction here to the case that R equals mu and omega is the identity map. To see that MUTS1 is MUP oriented. And so the following fact is kind of surprising. And here I thank Mark Behrens and Christian Reprise for a discussion where we realized this. That MUTS1 also admits an E-infinity map from the other MUP. Okay, so in some sense, MUTS1 is just such an insane thing to be looking at that it receives maps from both of the E-infinity structures on MUP. Okay, how do we see this? Well, a map, it suffices to produce, right? By this presentation, it suffices to produce an E-infinity map out of BU, sending the bot class to something invertible. By the adjunction, the GL1, the junction that I introduced in the beginning, that's the same as a map of spectra. Oops. Like that, but we did that in the first half of the talk. We can take the Euler-Tate Turin class, but for mu instead of the integers. And this thing had Hertzsprung series x plus ft over t, where now f is the universal form of group law of mu. But from this formula, you can check that the bot class basically goes to the, I think, coefficient of x in this expression, which is a unit. I think it's like t inverse times 1 plus order of t. And t is a power series element, so that's invertible. So we get the map. Okay. This also has the consequence, so Jeremy and Alan in that paper ask what forms of periodic integral cohomology are oriented by what forms of periodic Bourdism. And so now we find that ZTS1 is oriented by all three forms of periodic Bourdism. So these are all three, in some sense, mu, but with a periodicity element, and they all map in an E-infinity way to ZTS1. Okay. Another application. Let's fiddle with the representation again. Let's take G and the group. Let's take G equals CP, the cyclic group, and let's take as a representation W the regular representation. So we can sharp the identity of mu. To get a map like this. And hopefully it's believable that this map coincides as an E-infinity ring map with the Frobenius. And I thank the members of the Chicago Malort seminar for a great discussion on how to prove this. Okay. Should be believable, right? Because like the tensoring with the regular representation is the same thing as like the p-fold direct sum of vector spaces. So when you like tomify that, it becomes some sort of p-tensor power in mu, and we see Frobenius type stuff happening. And so what we immediately get from this like Hertzberg series stuff is a formula for the Frobenius coordinates. The image of the canonical coordinate of the Frobenius formula is no surprise to the experts. This is like the Euler class of L minus 1 tensor the regular representation. So you can see it looks, the k equals 1 term is exactly this, and then we just have higher k terms because, well, there are more irreducible summands of the regular representation. Okay, this formula has some nice consequences. First of all, this formula is insane because the universal formal group law is insane, and these K-series are insane. Oh, and the ring it lives in is also insane, right? This is MUTCP homology of C infinity. That's terrible. But you can actually glean some information out of it. First of all, you can like beam it into simpler rings. If you beam it into Eilenberg-MacLane spectra, you can like completely recover the evenly generated part of the dual Steenrod algebras. You can beam it into KO and get the Adams operations, formulas for the Adams operations from it. And I think, don't yet quote me on this, I opened up this formula, like the x squared coefficient of it, and looked mod decomposables, and I think you can prove that the first coefficient of any E infinity coordinate on MU that could be 0 is always 0. But I did that calculation on a beach 2 weeks ago, and no one has checked it yet, so don't use it. Okay, I think, yes, there's one more thing I wanted to say. So I have a picture to show. So, Eric Peterson, so we had the, yes, here, the Jacobi orientation is E infinity. So, Ando, Ando, Hopkins, and Resk build this machine in their paper that takes in number theoretic inputs, so these like congruent sequences of p-adic gadgets, and outputs E infinity orientations, and this is how they prove that the string orientations is E infinity. They prove some number theoretic congruences for Eisenstein series, and the output is the string E infinity-ness of the string orientation. Now we have this new E infinity orientation in the game, and we can run the machine in reverse. We can input the fact that we know that this thingy is E infinity and see what number theoretic congruences we get. And this was a recent work with Eric Peterson, and he made these beautiful diagrams. Colors are maybe a little hard to see. Certainly doesn't compete with Sarah's beautiful postcards, but I thought someone should give her a run for her money. Okay, so what are these? These are dyadic expansions, so two adic expansions of some coefficients of a Jacobi form, because it's the Jacobi orientation. And the fact that the Jacobi orientation is E infinity says that there's a bunch of congruences in this table. And so the colors are there to sort of help your eye see the congruences. The first one is that like all the numbers are like 0 mod p, so all the first digits in the first column are 0. More complicated ones happen as you go left. So like the most complicated one are these blue things. You get this long, I think it repeats after 16 something. Anyway, you get these like repeating patterns in the columns. These correspond to Kummer congruences. And so I found it very satisfying that this abstract nonsense with Tate constructions and stuff, you can at least, verify with a computer that it's not complete hogwash. Like the numbers check out. Okay, that's all I have for today. Thank you.
Question for a speaker?
Are these maps from MUP or MUP safe to MU safe? Do you know anything about those maps apart from the main?
Not much, yeah. So I wanted to know sort of more about the MU, like what the formal proof stuff is for the sharp one, this one. And then I sort of actively stopped thinking about it because we have this problem seminar in Chicago, and I thought it might be very suitable for the problem seminar to like figure out what's going on with this and that. So yeah, no, I don't know much. Well, actually, wait, I forget which it was. One of them I thought was suitable for the problem seminar.
I have two questions. First off, this formula for the Frobenius reminds me of a formula that's ubiquitous in Ando's work on power operations.
Yeah.
I assume that that's not a coincidence.
No, so as far as I understand that work is he's passing to the proper Tate construction and also passing further to E theory. And so the formulas are very similar.
Okay.
This also should very much remind people of like Quillen's elementary proofs paper where he calculates just the power operations, not the Frobenius, and he literally writes this formula.
Yes. And then my second question is, were these Kummer congruences, these p-adic interpolations of Jacobi forms previously known by the number theory community?
If I really want to know, I've been emailing number theorists. Oh yeah, so if anyone here either recognizes these numbers or these formulas or knows a number theorist that would, we would love to know. Yeah, we've been.
Is that on the archive?
Yes, this is on the archive.
Which paper?
It's called Eric came up with this nice title, P-adic congruences and iterated derivatives of P. P being the Weierstrass elliptic function. Yeah, so the short answer is I don't know. No. Homotopy theorists are always dying to make themselves useful to number theorists. So we really hope that the number theorists are one, interested in these congruences, and two, don't already know them. But who knows?
These p-adic congruences of Eisenstein series are so well studied. It seems
Yeah.
shocking that they hadn't thought of it. I mean,
We found some.
I could talk to you about some people to talk to.
Great, that'd be awesome. Thank you.
Anybody else? If not, let's thank you again.